Hi, and welcome back to Codex. Today's speaker is Professor Judith Packer from the University of Colorado, Boulder. Professor Packer studies the connections between wavelet and frame theory, operator algebras, and harmonic analysis. Today, she will tell us about wavelets coming from representations of graph C-star algebras. Take it away, Judy.
Thank you, John, and thanks all the organizers for inviting me. I haven't thought about wavelets for a while, so after I got this invitation, I have to start thinking about things again. And this is joint work that I did several years ago with Carla Farsi, my colleague, Elizabeth Gillaspy, who's now in Montana, Antoine Julien, who works in Norway, and Suran Kang, who's my former student now in Korea. So here I was, last month, thinking about wavelets. I said, I got to give this talk, but we were in South America, having a happy time, my husband and I. So, except that from this cold that got worse that I got in the joint meetings, but it wasn't COVID. So first I'm going to talk about directed graphs. Actually, our construction works for higher rank graphs where you have edges, multicolored edges, but I don't want to do that in this particular talk. It takes a while. And then I'll talk about the C-star algebras that come from these graphs. And then I'll talk about the wavelets that you can obtain once you make a particular representation of the graph C-star algebra. So by directive graph, I mean a quadruple E, with E0 being the vertices, E1 the edges, and range and source maps denoted by R and S. And for any edge E, the vertex S of E is the source, and that's where the edge starts, and the vertex R of E is the range, and that's where the edge stops. So here's an example. In this example, I just have one vertex V and three edges. And because each edge has to have a source and a range, all of these edges will be loops. They all start and end at V. My edges E1, E2, and E3. Here's another example that has three vertices and five edges. I haven't labeled the edges, but here are the vertices, V1, V2, V3. And E1 is a loop joining V1 to itself. E2 is the edge that joins V1 to V2. E3 joins V2 back to V1. E4 joins V2 to V3. And E5 joins V3 to V2. So my two examples, we'll come back to them often. So let's just get some little bit of, I see a chat question. Yes, it is me. Hi, Gusta. Okay. So a terminology here. I'm going to talk about finite paths and later infinite paths. So if we have a directed graph, a path of length 0, by that we just mean a vertex, and it's labeled V0, E0. And then a path of length n is a sequence mu equal mu1 through mu k. Oh, this n should be k, sorry. K should be n. And where we have the source of mu I, so the source of mu1 is equal to the range of mu2, the source of mu2 is equal to the range of mu3, etc., all the way up to here. The source of mu k minus 1 equals source of range of mu k. And E star is the set of all finite paths, this disjoint union of all finite paths that k goes from 0 to, and for all non-negative integers k. And then by the length of a finite path mu and ek, I denote that by d mu. So mu is my path. And you might be used to a different convention. In fact, if you look this up on Wikipedia, it is a different convention where we have the range of mu I equals source of mu I plus 1. Well, Ian Rayburn takes takes responsibility for that. He got into it, and in 2002 through 2005, insisted all the arrows and directions be switched. So if you read papers from the 1990s on this, all the directions are switched, and then he took charge and changed it. So we will be looking at the case where E0 and E1 are finite. And when can you concatenate two finite paths, mu and nu? Well, you can concatenate them from left to right if the source of mu is equal to the range of nu. Okay, and then if then the length of this concatenation will just be the sum of the length of mu and plus the length of nu. Okay. So here's some more terminology. If you have a directed graph, if V and W are vertices, then we denote by V, E, K, W, where K is a non-negative integers. All these paths of length K, such that the range of mu, the path mu, the range of mu is nu, and the source of mu is W. And then given a directed graph and a vertex V in that graph, we say the vertex is a source for V if V does not receive any edges. That means that the inverse image under the range map of V is empty. Well, we're not really interested in that case. That causes problems in our setup. So we say E has no sources if we have that we don't have a source. So you have to have at least one edge that goes into V, has V as its range. So we don't want that. But if you look at the papers like pre-2002, since all the arrows are reversed, they talk about graphs without sinks. Sinks are the bad things. But for us, after the arrows all got reversed, then sources became the bad things. Now we say a directed graph is strongly connected. If you have V and W that are vertices, you can always connect V and W by a finite path. So you will have a finite path such that the source of the path is W and the range of the path is V. And then we have the so-called vertex adjacency matrix of E. That gives a ton of information about your graph. So it's indexed by the vertices. It's a square matrix indexed by the vertices of E and having integer entries. So the VWth entry of this matrix will be the number of edges that go from W into V. So I'm mainly interested in the case where this particular vertex adjacency matrix has spectral radius greater than 1. And then we want the AE to be an irreducible matrix. That means, I guess, that for every n, or so for every V and W, you can find at least one integer n, such as the power, non-negative integer, such as the power AE to the n, has the VWth entry positive. So when we look back to our examples, the first example, we just have a 1x1 matrix with 3 edges, 3 loops. Well, that's just a constant matrix 3, and that's irreducible. And now in our second example, I've labeled the edges E1, E2, the vertices V1, V2, V3, and there are 5 of them. And then when you go through and calculate what the AE is, it's this matrix, which is also irreducible. The spectral radius is greater than 1. Okay, it's 1.802. We'll come back to this because this will be important. And in the higher rank graph case, where you have multiple colored edges, in that case, you have various vertex adjacency matrix, one for each color you're using, and we have that they commute. But as I said, that's for a different talk. It's hard enough to figure out this. Now we're going to talk about how to relate C-star algebras to the graphs, these finite graphs. So let's do a quick review of C-star algebras now. So C-star algebra A is a Banach algebra with involution, a star, and the involution and the norm satisfy this condition that the norm of A star A squared is equal to the norm of A squared for every A in your algebra. And so it's complete in the norm because it's Banach, and this is the C star condition. So examples of C star algebras are C of X, for X a compact Hausdorff space. And this one has a unit. You always want a unit. We don't always want a unit, but the ones we're studying will have a unit. The unit is a constant function. And then you have bounded operators on a complex Hilbert space. Okay, with the adjoint operation, that's your involution, that satisfies the condition. And then here's one that comes up when you're studying our graph algebras. In fact, if you take the universal C-star algebra that has two isometries S0 and S1 that satisfy Si star Sj is equal to delta Ij times the identity, and S0 S0 star plus S1 S star is the identity, is called the Cuntz algebra. O2 was first studied by Joachim Cuntz in the late 1970s. So,
Sorry,
this-
Judy, real quick, is there an excess square up in that definition?
oh, yes, thanks. This
Okay.
shouldn't be here. Thank you, Emily. This typo. The norm of A star A is equal to norm of A squared. And so non-commutative C-star algebras, this is commutative C of X, but if H has dimension greater than or equal to 2, B of H is non-commutative, and of course this is non-commutative O2. And so the non-commutative C-star algebras, then one wants to view them as somehow corresponding in a heuristic way to a non-commutative space. And then if you want to visualize your C-star algebras, with generators and relations, then C-star algebras corresponding to directed graphs amongst the first ones you would start thinking about. So let me say how to get these. Okay, so as I say, if you have matrix algebras, it turns out there's special cases of graph algebras, but you can visualize them via the matrix units, and you could have generators and relations. And then directed graph algebras were introduced by a lot of people, takes credit. Watatani and Fuji in the early 1980s were studying these. And then Kumji and Pask and Rayburn and were studying them in the mid to late 1990s. And then Rayburn gave a CBMS lecture series where that's the famous time where he changed the direction of all the arrows, which Wikipedia hasn't recognized yet. Right, so they generalized the Cuntz algebras of the late 1970s. They have these ON for every N. They're the Cuntz-Krieger algebras, OA, first studied by Kuntz and Krieger, that generalized Cuntz algebras. And then they're their matrix algebras. Well, all of them can be constructed as graph C-star algebras. So let's say how to get these with a finite graph. So the reason I want a finite graph is that then I can have a unit. Don't want to go too far out of bounds here. So you can study so-called row finite graphs where you don't have a unit, but I'm going to stick to the finite case. So if you have a finite directed graph, and again, I don't want any sources because it causes some problems, then you say you have a Cuntz-Krieger E family for that group, that graph. If you have a Hilbert space H and a collection of projections that are orthogonal for every index by every V in the vertex set, and a set of partial isometries on the H for every E in the edge set, and we want them to satisfy the following condition. SE star times SE should be the projection corresponding to the source of E. And then that's CK1. And then CK2 is that the projection corresponding to V is the sum over all E that whose all edges E, whose range is V of SE times SE star, whenever V is not a source, but in this case would be for every V. And then you're gonna, this of course would, when you sum these all up over all the V, they're orthogonal, they give you the unit for your C star algebra. So this is called a CKE family. It gives you a representation of the graph algebra. And then the actual graph algebra is generated by what we call universal Cuntz-Krieger E family, acting on some universal Hilbert space that satisfy the same conditions, but such that whenever you have any representation of the graph algebra, it factors through these universal generators for the edges and generators of projections for the corresponding to the vertices. So let's consider these universal partial isometry and universal vertices and what they should satisfy. Well, if you're in the setup where you have your finite directed graph without sources, and you let mu be a path of length k, then you can define a partial isometry in the universal, of course, from the universal partial isometries S mu corresponding to that path mu by just concatenating S mu1 with S mu2, etc. This should be a capital S, the script S. And if mu is a path of length k, you can verify that S mu star S mu is the projection corresponding to the source of mu k, and we generalize and call the source of mu the source of its final element here. So the mu starts over here with a source of mu k, ends over here with a range of mu1. And then you can verify that if you have a path of length j and a path of length k, and when you take these partial isometries and compose them, then you will get something that is non-zero, if and only if the source of mu is equal to the range of nu. That is, if and only if the paths mu and nu can be concatenated. And in that case, your mu nu is a path of length j plus k, and the partial isometries compose the way you want them to. They compose according to the path composition. Now here's the key thing. When you have E finite with no sources, C star E has a unit, and you can visualize it by having it just the closure of the span of S mu, S nu star, where mu and nu are finite paths, and S mu is equal to, the source of mu is equal to the source of nu. Okay, so this is what generates the C star of E. Now, in general, this C star of E would be infinite dimensional, but you can come up with simple examples of graphs where you get the finite dimensional case. I think I had this on the board. Might as well put it over here. I was going to add it in, but I thought it was too. This is the finite graph that gives you M4. It has 3 edges and 3 vertices. You could work it out and get matrix units. Okay. All right, so let's go back to our examples. Now remember, example 1 had 1 vertex and 3 loops as its edges. Well, it turns out in this case, you get your PV is just the identity, and your edges are SE, SE1, SE2, SE3 gives you isometries, regular isometries that satisfy SE star, SEJ, EI star, SEJ star is delta IJ times the identity. And then when you sum SEI, SEI star from I equal 1 to 3, you get the identity. Of course, this is just O3. If you think about it, this is O3. Now, what about our other example 2. Let's go back, take a look at it. Here it was. 3 vertices, 5 edges. Well, when you work it all out, here we have our 3 projections. They're orthogonal. They sum to be your identity. And your 5 partial isometries, they satisfy these 3 conditions. SE1, SE1 star, SE3, SE3 star is PV1. SE2, SE2 star plus SE5, SE5 star is PV2. And SE4, SE4 star is PV3. Let's go back to our vertex adjacency matrix that I was talking about before. So we have our finite directed graph, and then we have this finite matrix indexed by the vertices, and the VWth entry is the number of edges where the range of E is equal to V and the source of E is equal to W. Now, Cuntz-Krieger C star algebras are just C star algebras associated to directed graphs where the corresponding vertex adjacency matrix is a 0-1 matrix. So they were developed by Cuntz and Krieger in the late 70s, early 80s, and talked about described in a different way with all this graph material, but had universal generators and relations depending on the AE. And their representations have been studied carefully, and Kuntz algebras are a special case of these, and the people who studied such representations are Bradley and Jorgensen, Kawamura, Dutke and Jorgensen, and Marcolli and Paolucci have studied these. And we want to concentrate on the work of Marcolli and Paolucci from 2011, because they used a Perron-Frobenius theory on the incidence matrix to construct measures on Cantor sets that gave interesting L2 spaces for where they could have representations which had interesting properties, representations of the Cuntz-Krieger algebra. So we're going to review those. So let's talk about these wavelets. So what do I mean wavelets? Well, wavelets, of course, were defined in the 1980s, late 70s, 80s, etc., to give either one function or multiple functions whose integer translates and dilates by powers of 2 and then powers of other numbers, give an orthonormal basis for L2 of R. And then you had L2 of Rn, and then you would have integer translates and dilates by dilation matrices with all of whose eigenvalues were greater than 1 in modulus. Mallat and Mayer constructed the concept of multi-resolution analyses. And then, of course, Derbyshi's made these wavelets having compact support. Now, for us, wavelets mean something different, so that was slightly different, but it was coming from the work of Marcolli and Paolucci, who in turn used work of Alf Johnson. The idea was that the partial isometries generating some directed graph C star algebra should be viewed as generalized translations and dilations together. So the idea would be to obtain a finite collection of functions from an L2 space, such that when you moved it around by the dilations and no dilations and translations, but it would be partial isometries corresponding to paths, you'd get a basis, orthonormal basis for the L2 space. So this was the idea of Marcolli and Paolucci, who, as I said, generalized the work of Johnson. And the work done by Farsi, Gillaspy, and Kang and I, when we first were doing it, we were sort of saying, hey, we could do it for higher rank graph algebras too, the same idea. Okay, so let's talk about the measure space on which we will define the wavelets. So suppose you have a finite directed graph with no sources. What is an infinite path? Well, it's the same thing as a finite path, except you let it go on forever. So X is an infinite path if X is in this infinite product of edges. So you have a string of edges, one-sided string of edges, but you want the range of EIK equal to the source of EIK plus 1 for every K. Then E infinity is the collection of all infinite paths. And that's called the infinite path space corresponding to your graph. And then you can topologize this by using the so-called cylinder sets. In fact, you can see this already sits. E1 is finite, so you're taking the product of the E1s. This is already like a Cantor set. But let's use our finite paths because I want to use this notation. Suppose you have a finite path of length n in your corresponding to your directed graph. Then you call the cylinder into this path is called mu. Then you put brackets around it and say the cylinder set corresponding to mu is all the infinite paths such that the first n entries give you back mu. All right. And then after that, you don't have any restrictions on the entries of your infinite path. That's if n is greater than 0. And then if mu happens to be a vertex, v, then the cylinder set corresponding to that are the, this I think should say range, sorry, it should be an R. The mu or the x and e, so the range of E1 is mu, v. So this should be a range sign here. So these are a cylinder set, and they give you a basis for the topology on E infinity that corresponds to just the restricted, product topology from this set here. And this set here is totally disconnected, as is E infinity. So we're looking at totally disconnected sets, and they will be, this set will turn out to be closed in this set, and so it will be compact. So we have these compact ultrametric spaces, in fact. The graph E is said we really aren't interested in periodic graphs that don't have that cause us, to have to, if we have periodicity, we sometimes we would get on our measure space that certain vertices have measure 0. So we don't want that. But we say we have a aperiodic graph. If for each V in E0, you can find a periodic infinite path whose range is V. So let's suppose we have this finite aperiodic directed graph that doesn't have any sources, and we have a vertex adjacency matrix A sub E for it. Now it turns out that because of that, these hypotheses about the no sources and the aperiodicity, this AE will be an irreducible matrix. And then we will have the fact that you have this greatest eigenvalue non-negative and greater than 1 for AE. And therefore we can get from the maximum eigenvalue a non-negative eigenvector, the so-called Perron-Frobenius eigenvector for this matrix. This turns out to be very important in the study of the infinite path space because it allows you to put a very nice self-similar measure on the infinite path space. But the Perron-Frobenius eigenvector is a eigenvector for AE, which is indexed by the Cartesian products of the vertices. And then XE is indexed by the vertices. The entries are indexed by the vertices, and all these XEs are positive, and we normalize our vector so that the sum of all these vector entries are equal to 1. And that's going to give us a probability measure on the infinite path space. Okay. So here's the rule. The spectral radius is this largest eigenvalue, the Perron-Frobenius eigenvalue for A. And then when we let A sub E act on the Perron-Frobenius eigenvector, we just get this largest eigenvalue times the eigenvector. Definition of eigenvectors. And now here's this definition that comes from the work of Marcolli and Paolucci, and it can be adapted to the higher rank graphs, but here let's just talk about our finite directed graphs with one color for edges. So suppose we have a finite aperiodic directed graph without the sources and vertex adjacency matrix A sub E. Define a measure on the cylinder sets of the infinite path space by if mu is a path that is finite and bracket mu is a corresponding cylinder set, then the Perron-Frobenius measure of mu, you take that eigenvalue, Perron-Frobenius eigenvalue, raise it to the minus the length of mu, and then take x times the source of mu entry. And we call this the Perron-Frobenius measure on the infinite path space, and you can check it is in fact it's consistent, and it is a probability measure, because if you look at all the vertices, for example, they all each of the vertices are paths with length 0, and then when you sum up the measure corresponding to the cylinder sets of each vertex, you just get the sum of the entries of the eigenvector, which is 1. That's why we wanted the sum of our eigenvector to be 1 entries, so we would have a probability measure. This is called the Perron-Frobenius measure, and I guess the reason how it has a capital M rather than a mu is that the mu's were reserved for paths by the powers that be, and then when they wanted to have a measure, all they were left with were these Roman letters. Let's talk about, I think I skipped something, here, this is okay. In the example 2, here's what we have. We figured out our vertex adjacency matrix. Here, we popped this into some matrix, eigenvalue calculator and eigenvector calculator. Here's your eigenvalue, 1.802. Here are these eigenvectors normalized so that their sum of their lengths is 1. Okay, so mu of V1 is this 0.44505. Mu of the cylinder set V2 is 0.35690, etc. Mu of V3, M of V3 is this 0.198. And then you can correspond the measures corresponding to the edge spaces too, and I've written them all here. There's a lot of similarity here, but really there's some, when you take the disjoint union of 2 of these edge spaces, you get some of these other edge spaces. So that's when you do some of these sums, you can see they're related, that this plus this is equal to this, which is what you expect, because E1, the cylinder set E1 union cylinder set E3 gives you the V1, and so forth. And E4 corresponds to this over here. The cylinder, it turns out the cylinder set corresponding to the edge E4 is just the same as the cylinder set corresponding to the vertex V3. That's why they have the same measure. Okay, now that's our measure space that we'll use. L2 E infinity with this Perron-Frobenius measure. That's our Hilbert space. And then now we're just going to define some prefixing and coding. Coding is just the one-sided shift on your one-sided infinite path space. Prefixing is defined on subsets of the infinite path space, allows you where you are allowed to insert a finite path. So if you have finite path mu in E infinity, and you look at the cylinder set corresponding to the source of mu, then for every x in that cylinder set, you could put on a mu in front of it. So you have this so-called prefixing map, sigma mu of x is mu times x. And then you have the coding map, the one-sided shift, E infinity to E infinity. That's defined on all of E infinity. You just lop off the first entry of your infinite paths. So sigma, also denoted by sigma, but with no subscript, sigma v1 through ek is just e2, e3 on to ek plus 1. All right, so this is defined for every infinite path. You have this coding map defined everywhere. These prefixing maps are partially defined, but this sigma coding map can be concatenated with itself, composed with itself arbitrarily many times. And then you can check that when you do sigma p, the coding map composed with itself p times, and compose that with sigma mu of x, whenever x is in the cylinder set corresponding to the source of mu, then you just get partial inverses here. Sigma p, sigma mu is equal to x for every mu in E in the paths of length p, and for every x in the cylinder set. And then you have, whenever the source of mu is equal to the range of nu, that you can concatenate these prefixing maps and get what you expect. So these are maps, measurable maps. These are only partially defined, of course, but the sigma, the one-sided shift, is defined everywhere on the entire infinite path space. And we use these maps to define our representation of the graph algebra, graph C-star algebra. Okay. So this is, I've stated it here as due to us, but this is really Marcolli Paolucci, and then we did it for higher rank graphs. This is a 4-author paper published in 2017. If you have a finite directed graph with no sources, and you have these prefixing maps and the coding maps that I defined earlier, this is just concatenation of sigma with itself p times. Then you can define partial isometries and orthogonal projections that satisfy the Cuntz-Krieger relations for the directed graph on L2 of E infinity with respect to the Perron-Frobenius measure. So we have S mu of course, x on a vector C, a function, but you take the characteristic function corresponding to cylinder set mu, and then you need to have this Perron-Frobenius spectral radius here and raise that to the 1/2 power. And then you have sigma, and you do the coding map just once here, do a one-sided shift. And this is mu of course, an edge. So that's why we have ones here. But of course, if mu was a path of length p, you might have other formulas here. We have p here. And then the projection corresponding to vertex v is just characteristic function of v of the cylinder set v of x times the function c of x. Then these operators generate a representation of the Cuntz-Krieger algebra C star v. Well, it's not the directed graph algebra C star v. If v is aperiodic, this representation turns out to be a faithful representation, which is nice. Again, another reason to like periodicity. And this can be generalized to higher rank graphs. Well, let's talk about an example where this, as you recall, gave us our Kuntz algebra O3, our first example, 1 vertex and 3 edges. If you have any infinite path in E infinity, it's just this looks like this, where you just have arbitrary choices of the edges here. So it's really the Cartesian product of the index set 1, 2, 3 infinitely many times. And here you can check that your Perron-Frobenius measure is such that the index here, we just had the 1-by-1 matrix with single entry 3. So we get our equidistributed or measure that the measure corresponding to each edge set is the same, 1/3. And then here's what our pure isometries do in this case. They look like this. You have square root of 3 times characteristics. If you have SEI and you let it act on a function C, this is what you get. I've written it here. You have square root of 3 times the characteristic function of a cylinder set EI times this sigma with the one-sided shift acting on the X. And you could verify that the Kuntz relations are satisfied for O3. Okay, so now let's review the wavelets. The wavelets finally come into play. So Marcolli and Paolucci, motivated by work of Johnson, who was describing wavelets corresponding to only some dilations and some translations on the fractal set, they developed their wavelets corresponding to the Cuntz-Krieger algebras and get a wavelet decomposition. Of course, here your E infinity is a compact set, so you really, each of these subsets in the multi-resolution analysis that we will get will turn out to be finite dimensional because we have finite graph. And if time permits, we'll talk a little bit about this Laplace-Beltrami operator material. So to construct the orthogonal subspaces of L2 E infinity, the initial space will be the space V0 that is spanned by the characteristic functions corresponding to the cylinder sets coming from vertices. But we need this measure here. We use these, we have these formulas here so that we can get the measure. So we have unit vectors here. We divide by the square root of the measure for each vertex times the characteristic of the cylinder set corresponding to the vertex. And that's has this, you will have cardinality V0, many of these functions, and they span your V0 set. So they're the quote scaling functions. And okay, I'm looking at this note. They span V0. Now to construct the so-called wavelet zero set W0, you first use fictive vertex in E0, then let dV be the edges whose range is V, and let little dV be the cardinality of big dV. And now we're going to construct an orthonormal set for each dV. And remember, we have our Perron-Frobenius eigenvector. Well, that we can use this to define an inner product on C dV, complex numbers dV times, like so. Here we have these, we're just using the entries of the Perron-Frobenius eigenvectors whose ranges are V. Those are the only ones we're interested in. And we use that to construct this inner product. And then find an orthonormal basis in C dV that is the orthogonal complement, that spans the orthogonal complement for the constants vector 1, 1, 1, 1, 1. Because that sort of corresponds, the 1, 1, 1, 1, 1 corresponds to your characteristic function of the vertex set V, because you're sort of taking the sum of the characteristic function of the edges cylinder set, whose range is V. Well, that turns out to be the characteristic function for the cylinder set corresponding to V. So when we take all of these, of course, if you only have dV equal 1, then you just have you don't have to worry about the C, about finding any of these, you're done. But if dV is 2 or greater, then you get these vectors, and they give you your wavelets. Here they are. And they turn out to be orthogonal to all the characteristic functions corresponding to vertices. If V if W is not equal to V, they just are disjoint from one another. So that you take the product with characteristic function of W and you get 0. For V, we've worked it out so that when you take this times this, you're going to get this inner product thing to be 0. So here's what you get. They are an orthonormal set L to infinity. They're finite dimensional, and when you take the span of all of them, where you range over all the possible vertices and all the m going from 1 to dv minus 1, and of course if dv is 1, you don't have any contribution from that v, that's your W naught, the wavelet subspace. And here's the second theorem, which can be generalized to higher rank graphs as well. And that tells us that you can define, we have the V0 and the W0, but you can define sets Wj by moving these paths by mu, by the partial isometries corresponding to paths mu. You move the wavelets by the partial isometries, and if j is greater than or equal to 1, you get things that are orthogonal to V0 and to W0, and they're orthogonal for each other for J1 not equal to J2, and they span the entire space L and L2 of E infinity. Because basically the span of the cylinder sets is dense here, and you can get any cylinder set by taking a linear combination of finitely many ones of these. So that's how you get these this density. All right, so wavelets in example 2. I have 3 scaling functions, one for each wavelet, one for each vertex. Then it turns out when you do this construction, dv1 has 2 elements, dv2 has 2 elements. So these two will contribute 1 wavelet each. dv3 only has 1 element, so it won't contribute any wavelets, but here are the 2 wavelets we get here. The kappa 1 and the kappa 2 are just constants that real constants that you get so that these wavelets have unit norm. And they look like this. Please notice that the measure of this E1 cylinder set is this value here. The measure of this E3 cylinder set is this value here. And that's sort of why they're orthogonal to the phi1 here in this case. And ditto for this, why this one is orthogonal to this one. And I think I'm coming to the end. The Kuntz algebra ON, we've already seen O3, but you can also obtain it from getting a direct graph, EN directed graph that has n vertices and n squared edges, and the n by n transition matrix has all the entries equal to 1. And then this Perron-Frobenius measure satisfies the measure of a cylinder set corresponding to a vertex is 1 over n for every vertex. And then when you set up your infinite path space, it just looks like so. It's just the infinite product of Z mod n. And when you go through the standard construction, you get the V0 has n scaling functions, and each W0, there's n times n minus 1 of in W0, the span of n times n minus 1 functions. Here's the Wn, and you get this so-called wavelet decomposition, which turns out to be very similar to decompositions you would know about from other methods, I believe. And this is a classic, coming from the classic monic representations of the ON due to Dutke and Jorgensen. Okay, I think I'm running out of time, so I don't really have time to talk about the spectral triples aspect of things. But I should just say that these, instead of infinite paths, I'll draw a picture here for O2. Pearson, Belisard, Julien, and Savinian like to think of Michon trees, and then they weighted these Michon trees, and the boundary of the Michon trees corresponds to the infinite path in our case. And the weight on these Michon trees comes from the Perron-Frobenius matrix. So when I showed our wavelets to Antoine Julien, he said, "Oh, these just look like your wavelets. Just look like the kernel of our Laplace-Beltrami operators that we obtained from non-commutative geometric methods." And lo and behold, they were. They could be connected under the appropriate conditions. They could be related and identified. That the V0 came from Laplace-Beltrami, and the Wn all came from kernel of Laplace-Beltrami. Here is just for O2, but it's true in greater generality and for these higher rank graphs. So I'm going to stop there. I think you could read about the non-commutative geometry if you want to in these papers, because it has come out. But I will stop there because I'm over time. But thank you for your attention.
Thanks so much, Judy. So I'd encourage everyone to hit their reaction button. We're all familiar with this by now. And if there are any questions, feel free to chime in.